Hello, I am Seema and welcome to part 25 of the chapter Hydrocarbons. We were doing the chemical properties of alkenes and picking up from where we left off, I'll now be explaining the third property, that is addition of hydrogen halides to you. Hydrogen halides like hydrogen chloride, hydrogen bromide and hydrogen iodide can add to an alkene. I told you in the previous video that alkenes have got the pi electrons, that is the second bond are pi electrons which are loosely held, and therefore attacking regions, usually especially electrophiles, they come and attack this source of electrons, and therefore electrophilic additions do take place in the case of alkenes. So this is an example of an electrophilic addition reaction. And in the alkyl halide or the hydrogen halides, not alkyl halides, the hydrogen halides, the halogen part is the negative part and the hydrogen is the positive part. So the electrophile in these cases is actually the positive part. So all these halides, hydrogen halides, they break down into H positive and the halogen negative, X negative, it could be I negative, Br negative or Cl negative. And the H positive attacks the double bond first because it's an electrophile, it loves electrons, and the pi electrons, the loosely held electrons which are available, which can easily be, that second bond can easily be broken and the H positive can come and attach itself to one of the carbons. And then in the next step, the halogen, whichever carbon the hydrogen attaches itself to, the halogen then comes and attaches itself to the other carbon. And that is how you will get the addition of the hydrogen halide takes place. It will become clear as we understand the whole topic. So when addition, I also told you in the previous video that in the case of the hydrogen halides, if you see the rate of reaction, the addition of hydrogen iodide is the easiest. Then comes hydrogen bromide and then HCl. The reason for this is that HCl is far more stable and therefore ionizing it or breaking it down would not be as easy. And hydrogen iodide, the size between the hydrogen and iodine is, the difference is quite large, and iodine is not as electronegative as chlorine. Therefore, there the breaking is easier, and that's the reason why this shows the fastest rate of reaction. Now, addition of hydrogen halides can take place to either symmetrical alkenes or unsymmetrical alkenes. What does a symmetrical alkene mean? An alkene which has the same number of carbon atoms on both sides of the double bond would be a symmetrical alkene. Take a look here. This is the double bond. On this side of the double bond you have one carbon and on this side you have one carbon. Here also in the second symmetrical alkene you have a double bond here, and on this side of the alkene you have two carbons and on this side you have two carbons. So it has an equal number of carbon atoms on both sides. That would be known as a symmetrical alkene. So what would an unsymmetrical alkene be? From the name you can understand that if symmetrical means equal number of carbon atoms on both sides of the double bond, unsymmetrical means an unequal number of carbon atoms on both sides of the double bond. So the addition can take place to symmetrical alkenes or it can take place to unsymmetrical alkenes. But we see a little difference in the behavior. It is actually the same reaction, the same process is going to take place. But when the addition to unsymmetrical alkenes takes place, there is a possibility of more than one product. Therefore, we study it separately. In the case of symmetrical alkenes, the product is always the same. Therefore, we don't bother about explaining all of it. You'll understand it again as I keep explaining this. So look here, this is ethene. Ethene has got a double bond between two carbon atoms. If you add HBr to ethene, what is going to happen? The hydrogen is going to add to one of the carbons and the bromine is going to add to the other carbon. So we see here the CH2 becomes CH3, so hydrogen added to this carbon, and to this carbon the CH2, the Br added to this carbon. So you got CH3, CH2, Br. What's the name of this compound? It is bromoethane. Let us assume that the hydrogen had attacked this carbon instead. Then the formula, the compound that I would have got would have been BrCH2CH3, right? The compound that I would get would be BrCH2CH3. Now look at this compound and name it. Is it any different from this compound? It is not, because if I name it now, I would still call it bromoethane. Here also I called it bromoethane because the carbon having bromine would become the first carbon. Therefore, this is the first carbon, this is the second carbon, and this is one bromoethane. And here also, even if the direction is the other one, I will still start numbering or giving the locant here. The lower locant would be 1. Therefore, this would also be 1 bromoethane. Since you get the same product, we don't bother about making the different. You are getting just one product here. The second example here is butene, but2-ene. But2-ene is symmetrical. Why? Because the second carbon and the third carbon have double bond. Even if I count from this side, the second carbon and the third carbon have the double bond. Therefore, one of these carbons will have hydrogen, one of these will have bromine, and you will get just one product which would be 2-bromobutane. Right? Let us assume that the bromine had added here and the hydrogen had added here. It would still be called 2-bromobutane because now I will be counting from this side. So, what do we understand from this? That when addition of the hydrogen halide takes place to a symmetrical alkene, you get only one product. To one around the double bond, one of the carbons gets the hydrogen and the other one gets the halogen. And you get the halogen derivative of that alkane. So that was addition to symmetrical alkenes. Now, let us see what happens when addition takes place to unsymmetrical alkenes. An unsymmetrical alkene, for example, is propene. In the case of propene, why is it unsymmetrical? Because these are the two carbons having a double bond. On one side of the double bond, you have only one carbon, but on the other side of the double bond, you have two carbon atoms. So it is unsymmetrical. Now, it will make a difference which carbon is the bromine adding to. If the bromine, hydrogen adds to this carbon and bromine adds to this one, you will get 2-bromopropane. But if the hydrogen adds here and the bromine adds here, you will get 1-bromopropane. So you will get two different products depending on which carbon is the bromine going to go and attach itself to. It has been seen that usually when you carry out this reaction, it is 2-bromopropane which is formed in a greater abundance, and 1-bromopropane, the quantity of 1-bromopropane is very, very little. If you really think mathematically, you are just putting molecules together. You had the propene molecules and you had HBr, they are hitting each other and they are reacting with each other. When they are reacting each other, logically, according to your mathematical, what permutation and combinations, I don't remember what, your probability. The probability of having both the forms or both the products should be 50-50%. You should get 50% of this and 50% of this. But we find that one of the products is dominating, and this is very little, it's very minuscule. The major product is 2-bromopropane. How do we explain this? Why is one product being formed, is being preferred over the other? This could be explained, this was explained by a scientist called Markovnikov. And he explained this in 1869. In the year 1869, he gave a rule which was known as the Markovnikov rule. And Markovnikov's rule was he gave this rule to explain why one of the products in an unsymmetrical alkene is favored and the other one is not. So what was the Markovnikov rule? Let us read the statement. 1. You remember I told you that this addition is an electrophilic addition. And I also told you when we talk of electrophile, in the case of a hydrogen halide, the electrophile is hydrogen. H positive is positively charged, therefore that will be attracted to electrons. So the electrophile here is H positive. And the Cl negative is going to add as a second step. So he said that the negative part of the addendum. Addendum is that substance which is adding to the alkene. So whatever is being added, that is an addendum, a little fancy term, makes you feel a little more scientific to say, that's the addendum. When you say to your friends or someone who doesn't know chemistry, they might feel that you're really giving a very good, you really know a lot of chemistry. Jokes apart, addendum is that molecule which is adding. So the negative part of the addendum, which one would it be in the case of HBr, which is the negative part of the addendum? The positive part is H positive and the negative part is Br negative. So the negative part of the addendum, that is the adding molecule, gets attached to that carbon atom of the double bond, that carbon which possesses lesser number of hydrogen atoms. Look at this now. Which one has lesser number of hydrogen atoms? This carbon has 1 hydrogen and this carbon has 2 hydrogens. So according to Markovnikov, the product in which bromine, which is the negative part of the addendum, adds to the carbon which has lesser number of hydrogens will be more stable. This, as a rule, it has been seen that that carbon which has lesser number of hydrogens will have the halogen atom attached to it, and that will be more stable. How could he explain this? What was the explanation? All right, you gave a rule. Look, anyone who has lesser number, or let us say it's a race and goodies, freebies are being distributed, food, biscuits or something is being given to people who are running in a marathon. And the number of biscuits, that is bromine, is the, let us say, is the freebie, the biscuit. Bromine is going to go to that carbon, that runner who has lesser number of biscuits, or not biscuits, lesser food. So the negative part of the addendum goes to that carbon which has the lesser number of hydrogens. The reason, what could be the reason? The reason can be understood if we understand the mechanism of this reaction. So let's understand the mechanism. What happens in this reaction? And once we understand what happens, we get to know why exactly does Markovnikov rule take place? Why exactly does addition take place according to Markovnikov rule? So the mechanism, the first step is the formation of an electrophile. It is an electrophilic reaction. So the first step in an electrophilic reaction is, how can a reaction be electrophilic if there is no electrophile? So the first step of any electrophilic reaction would be the formation of the electrophile. So HBr will break down into H positive and Br negative. And H positive is positively charged, therefore the electrophile is H positive. Now, in the first, the electrophile was formed. In the next step, the electrophile will attack the alkene. It will come and attack the double bond of the alkene. So this is not a reaction that takes place in one step. It takes place in 2 steps. Or you could say 3 steps. The first step being the generation of the electrophile. The second step being that the electrophile attacks the alkene, and it is the electrophile which adds to it first. So when you have HBr, the H positive of the HBr attacks the alkene, and you get 2 products, obviously. The H positive, this second bond will break, and the H positive can either add to this carbon or it can add to this carbon. So when it adds to this carbon, you will get CH3, CH2, CH2. Do you see? This is H positive. H positive means hydrogen has only 1 electron. If it loses that electron, it becomes H positive. What is the second bond? The second bond is a pair of electrons, right? So now, when this H positive comes and attaches itself to this carbon, the H positive comes and attacks this carbon by it will take both the electrons, because it is positively charged, it will take both the electrons of the pi bond. And since it takes both the electrons, where did the 2 electrons of the pi bond come from? The 2 electrons of the pi bond actually belong to the 2 carbons. This carbon had 1 electron, this carbon, they shared that pair of electrons. Both of them shared their electrons to form the pi bond. When the bond breaks, in a homolytic cleavage of the bond, both the carbons should get back their electrons. This does not happen here. What is happening? Since the attacking reagent was an electrophile, it is positively charged. When it comes and attacks the carbon, it takes both the electrons of the bond. When it takes both the electrons of the bond, one of the electrons had belonged to this carbon. So what happens to this carbon? It now becomes deficient in one electron. Since it becomes deficient in one electron, the positive charge comes on this carbon. The carbon that lost its electron. It had only shared its electron in the formation of a pi bond. But then came the attacking agent, the electrophile. It came and it took both the electrons. So this carbon wasn't lost, it became positively charged. Such a species which has a positive charge on the carbon in the hydrocarbon is known as a carbocation. It is a carbon compound, but now it is a cation because it is positively charged. So it is known as a carbocation, right? So a carbocation is formed, and of course the Br negative was formed, that is still there in the reaction mixture. The other possible product would have been that the H positive did not attack this carbon, it attacked this carbon. The same thing will happen. The cleavage happened, the H positive came and attacked this carbon, and when it came and attacked this carbon, it took both the electrons and formed CH3. But the poor carbon in the middle who lost its electron now becomes positively charged. So now this carbon becomes positively charged and Br negative is formed. So this is also a carbocation. Now what is the difference between these two carbocations? This carbocation has carbon, is present, the positive charge is on a carbon which is attached to only one other carbon. But this carbocation has the positive charge on a carbon atom which is attached to two other carbon atoms. Which means this is a primary carbocation. The positive charge is on a primary carbon. A primary carbon is one which is attached to only one other carbon. And here, this is a secondary carbocation. Why? Because the positive charge is on a carbon which is attached to two other carbon atoms. So you get a secondary carbocation. A secondary carbocation is more stable. Why is it more stable? Imagine if there's a positive and a negative charge. The positive charge is on one end. The negative, or imagine the positive charge to be like a ball of iron. It's a heavy ball. So if I'm lifting a ball, a heavy ball in my hand, let us say in my drink, it's heavy and I have it on one hand and it's really heavy and it's pushing down at my hand. So it's a little imbalanced because now it's pushing down on the edge. But if I have the ball of iron or my drink on top of my head, it is not affecting the arms. It's a more balanced structure. So it is more stable. It will be more stable if the weight is on the weight, or in this case, what is it? It is positive charge. Wow. So that's positive charge on the second carbon, that is the secondary carbon. Therefore, a secondary carbocation is more stable. Whenever you have an ion which is more stable, it will be formed faster. It is a marathon race, you remember? Anyone who is faster would obviously win the race. So you have millions of molecules in the mixture, but most of those, they will try to form the secondary carbocation. They will not try to form the primary carbocation because the primary carbocation is not that stable. So you will get a major amount of the secondary carbocation. And at this step itself, it is fixed which product is going to be the major one, right? The secondary carbocation will be formed more. Therefore, whatever product is formed by the secondary carbocation will be the major product. So what will be the product? The next step is after the electrophile was added, now the nucleophilic part, that is the negatively charged bromine now, that will attack the positively charged carbon. The molecule has to be neutralized again. So it has formed cations, but as soon as the cations are formed, the negatively charged bromine present in the reaction mixture will attack that positive part, that positive carbon. It will form a bond there. Now since bromine is Br negative, it has an extra electron. Since it has an extra electron, it will use 2 electrons to form the bond with the carbon which is positively charged. So this one will form 1 bromopropane. If the bromine comes and attacks this carbon and it attaches itself here, it will form 1 bromopropane. And this one, when the bromine attacks the second carbon and forms CH3, CHBr, CH3, which is formed here, it forms 2 bromopropane. And that is the reason why 2 bromopropane is the major product. And that is the reason why it was noticed that whenever you carry out the addition of a hydrogen halide to an unsymmetrical alkene, you always get one of the products as the major product. And that was the observation because of which it was made into a rule that it has always been seen that the negative part of the addendum will always add to that carbon of the chain which has lesser number of hydrogen atoms. Simple, that is because it is forming a more stable carbocation. The more stable carbocation will lead to the addendum, that is the negative part of the addendum, adding to that carbon. In this case, it is the secondary carbocation. So that was Markovnikov rule explained. Now, it has been found in the presence of peroxide, the addition takes place against Markovnikov rule. It is known as anti-Markovnikov addition or Karash rule. We'll understand that in the next video. So if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and if you wish to watch the other videos of this chapter, please click the link that has appeared over your screen on the top. And thank you for watching, and bye-bye for now.